Good afternoon, everyone. Welcome to the third lecture of NITheCS Mini-school on From Physics to the Machine Learning and Back Again. And today we're very fortunate to have a Professor Vishnu Jejjala with us from WITS. And he will tell us about the machine learning of the geometry of the space-time, and as it's applied to a little bit of corner of his academic interest, which is more related to the kind of fundamental questions of physics and high energy physics. And Vishnu get his PhD from University of Illinois, Urbana-Champaign in 2002. Afterwards, he proceeded with several postdocs in Durham, Virginia Tech, and in Queen Mary University of London. And afterwards, he joined, in 2011, he joined the WITS University, and he got also the South African Research Chair in Theoretical Particle Physics and Cosmology. And now he's still there. He's also a professor in the School of Physics. Okay, Vishnu, we're looking forward to your talk.
Thank you. So I'm glad to be here. I hope that people will interrupt as necessary and ask questions because I want this talk to be somewhat didactic. I'll tell you a little bit about some ideas I've been thinking about research-wise and the utility of machine learning as a tool to study these sorts of problems. So let's begin by discussing what we know about the world. We know that there are interactions between particles and masses, and these are well described by two different ideas. One idea is general relativity, which is our description of space-time. It tells us how geometry responds to the presence of matter and energy, and conversely, how the presence of matter and energy in a curved space-time is responsible for how things move within this background. So the Einstein equation is something which is extremely well tested. It's been tested from cosmic scales, the size of the universe, to micron distances using these torsion balances, these Cavendish type experiments. So it's an extremely well-tested theory that we think we understand extremely well. The other set of interactions that are somewhat fundamental are the interactions of fundamental particles. Elementary particles are described by the standard model of particle physics, and it encompasses electromagnetism, the weak force, which explains radioactive decay, the strong force, which explains how protons and neutrons are put together, and the Higgs effect, which endows particles with their masses. So this is the best tested theory in the history of science. No experiments invalidated this, and everything that we've seen at the Large Hadron Collider and similar particle experiments are all consistent with the structure of the standard model. We think the standard model requires that there be new physics to explain the entire story of particle physics. So the standard model is for the beginning, but not the ending. And the reasons for believing this is things like matter-antimatter asymmetry in the early universe. This can't be accommodated by the amount of CP violation in the standard model, for example. So we think there must be new physics to find. But nevertheless, this is the starting point for investigating particle physics. The goal of many physicists, Einstein famously among these, was to come up with a unified theory that explains both the gravitational interactions and the particle physics interactions. And this has been an outstanding challenge to come up with a framework that enables us to unify all the forces that we know. So one of the difficulties is that non-gravitational interactions are not encoded as geometry. This is, in some sense, the content of the famous Coleman-Mandula theorem, which says the symmetry group in 4 dimensions is Poincare. Symmetry is associated to, say, Lorentz transformations and internal symmetries. The loophole is that internal symmetries can arise from higher dimensional geometry. So one of the first manifestations of this was in Kluser-Klein theory, which was discovered and elaborated upon in a decade after Einstein's theory was first proposed. And the idea is that suppose we consider flat space with an extra circle direction, a fifth dimension. If you consider Einstein's equations in this five-dimensional space, and there's no source, there's no energy momentum tensor in 5 dimensions. So the right-hand side of Einstein's equation is explicitly 0. If you consider the effective theory in 4 dimensions, you make a circle that you've introduced small radius. The effective theory in 4 dimensions gives you Einstein gravity, the equation at the top of the page, where the source on the right-hand side, the energy momentum tensor, is the energy momentum tensor associated to electromagnetism, i.e. The Maxwell equations. So in 4 dimensions, gravity plus the Maxwell equations come for free in a sense, if you consider an empty 5-dimensional theory on this space, which is 4-dimensional flat space with this compact circle. So this is sort of a paradigm for how to describe gauge interactions like electromagnetism in nature using just purely geometry. And this idea is a recurring idea that we'll return to in the talk. So the 5-dimensional geometry, the geometry of the higher dimensions, tells us about physics in lower dimensions. And this is a thematic idea which is central to our views of modern physics. So the best theory we have for quantum gravity is string theory, and string theory is a way to reconcile tensions that exist between quantum field theory and gravitation. If you treat gravitation as an ordinary quantum field theory, you run into problems. So the Feynman diagrams involving exchange of gravitons, if you add enough of these up, you'll find this is always divergent. So in a sense, the force between two masses in a quantum field theory of gravity is always going to be infinite. So one way to render these Feynman diagrams finite is to smear out the interaction. In the smearing, instead of thinking about particles as being point-like, you think about particles and the exchange particles as well, the gravitons, as being little loops of string. If you treat these interactions by smearing them out and think in terms of these loop interactions involving these strings, these Feynman diagrams will turn out to be finite. The consistency of these theories, however, requires you to work in 10 dimensions rather than 4 dimensions. So we see that string theory, our theory of quantum gravity, tells us that we should be thinking in higher dimensional spacetimes. And moreover, the consistent movement of the string in a particular background gives us the Einstein equations in that background. So the string moves self-consistently in the background that it generates, and this is in some sense the origin of gravity in the target space-time. So we have in our best model for quantum gravity a higher dimensional space, and we want to see what the implications of higher dimensional space is for physics in the 4-dimensional world that we observe. And we'll use the Kaluza-Klein idea to say things about this. So string theory is in fact a web of interconnected theories, and these theories live in 10, 11, or 12 dimensions. And we'll focus on the 10-dimensional corner here of this this web. So the higher dimensional objects, in addition to strings, exist in string theory. These objects are called branes, the generalized membranes, if you like. And we'll make an ansatz for what the 10-dimensional geometry is. Just like Kaluza-Klein ansatz was that we had R1, 3 plus a circle. Here we'll have R1, 3 times a compact space. And the properties of this compact space, which is called Calabi-Yau, describe physics in 4 dimensions at low energies that we observe, just like the dimensional reduction of the 5-dimensional Kaluza-Klein theory told us about physics in 4 dimensions and gave us gravity plus electromagnetism. So in particular, in the very simplest models for string compactification, topological properties of this Calabi-Yau will tell us about the number of generations of particles, for example, in the standard model that you obtain upon compactification of this 10-dimensional theory down to 4 dimensions on this small space. And in fact, this is sort of the origin of this, this whole subject of string phenomenology. How do you reconcile the real world with string theory? So things are slightly more complicated, of course. We don't really live in flat space. Our universe most closely approximates de Sitter space, and we have much less understanding of de Sitter space's origins from a stringy framework. So there are certainly open problems to consider, even within this context of geometrical engineering of 4D physics from 10D. Okay, so what we have, where we are right now, is that string theory supplies a framework for quantum gravity. It's an architecture that embeds many possible quantum field theories in 4 dimensions that are consistent with seeing gravity in space-time. And we're beginning to understand aspects of this, this in terms of black holes. For example, we made lots of progress in understanding the structure of these string theories. String theory has also had a great deal of success in understanding mathematics. In fact, every cool result in mathematics somehow finds a home in string theory. So in many ways, string theory is an organizing principle and also a way to discover new mathematics. And the difficulty is in finding our particular universe among the space of possibilities. This has many different names. It may be called a landscape problem, the vacuum selection problem. So the idea is that if we start off with 10 dimensions, and there are lots of these Calabi-Yau spaces, for example, how do we choose the Calabi-Yau in order to recover the 4-dimensional space that we see? In the Kaluza-Klein reduction, there was essentially a unique idea of having a circle in order to recover electricity and magnetism, because the gauge group of electricity and magnetism is U1, and U1 is the group of phases associated to a unit circle, so the circle is very, very natural there. There's similarly no simple idea for how to realize, say, a standard model group structure from these compactification manifolds a priori, essentially uniquely. So we have to work harder in order to determine how to go down from 10 to 4. Most choices we make don't resemble nature at all. So the choices that are involved may be somewhat subtle. And among all the possibilities, there is none which covers both the particle physics aspects that we're after and the cosmological aspects that we're after. So we'll begin, rather than looking for the real world, we'll look for the unreal world. But we'll look for an unreal world which is, in some ways, a cousin of the real world. So hopefully, what we learn by constructing and playing and engineering these particular quantum field theories I'll discuss are amenable to lessons about how to obtain the real world eventually. So we'll look for particular extension of the standard model called the minimal supersymmetric standard model. And the minimal supersymmetric standard model admits the same sorts of particles that we see in the standard model. And when supersymmetry is broken, perhaps it gives us a standard model. The minimal supersymmetric standard model certainly has not been excluded by experiment. So it's certainly possible that future experiments will see aspects of the structure in observation. But the idea is that we have the same particle structure and interactions as in the standard model, except there's this supersymmetry. So supersymmetry says that for every boson in nature, there's a fermionic partner and vice versa. And these particles are mass degenerate, since we don't see a scalar electron as a counterpart to the ordinary electron. We know the symmetry is broken in nature if it exists at all. But this is where we'll start. We'll consider theories with supersymmetry in nature. And it turns out that because these compact manifolds are described, these Calabi-Yau, they admit a Ricci flat metric. The flatness of the compactification space in a suitable sense enables us to have four-dimensional supersymmetry. So this is a feature of this geometry that we're using for string compactification, that the structure is there. So we'll try to understand how to realize aspects of the structure geometrically as this talk proceeds. Already we've seen that topology, not geometry, is enough to constrain certain aspects of particle physics. For example, a number of generations of particles in the standard model is described by the topology of these manifolds rather than geometry of these manifolds. So here's a picture of the simplest Calabi-Yau. We're looking at actually slices of this into three real dimensions. The Calabi-Yaus have a precise mathematical definition. Precise mathematical definition is that on this manifold, there's nowhere vanishing holomorphic n-form for a Calabi-Yau n-fold. So for the Calabi-Yau three-fold I've shown, this is a nowhere vanishing holomorphic three-form that exists. There are other equivalent definitions that I've written down as well. Okay, so what we don't know about these Calabi-Yau spaces is what the flat metric actually is. We know that such a thing exists as the content of Yau's theorem. We don't actually know what it is explicitly. So we need to use numerics in order to write down metrics that are Ricci flat on these Calabi-Yau spaces. And that's where machine learning will enter into our story. So just to step back a little and describe these constructions of the minimal supersymmetric standard model from string theory, there are numerous such constructions. Maybe 10,000 of these are known at some level of detail. And by this, what I mean is there's a correct matter spectrum and the correct interactions, and the actual couplings which appear in the Lagrangian, however, are not known. We just know that certain terms are present in the Lagrangian. So these constructions were developed using only topological features of the Calabi-Yau. We didn't actually have to know metrical features. We didn't need to know the Ricci flat metric in order to accomplish these constructions of standard model-like theories from string theory compactified on these Calabi-Yau spaces. However, if you want to do phenomenology, if you want to understand how supersymmetry is broken from the minimal supersymmetric standard model to get to the standard model, we need to know these metrical features as well. We need to know this flat metric. So in order to have kinetic terms for the matter, we need to have the structure, this geometric structure explicitly known. In order to solve for these couplings in the Lagrangian, in principle, to solve for the mass of the electron in one of these theories, we need to know what the flat metric is. We also need the flat metric for issues like moduli stabilization to ensure that the framework we developed is stable in some sense. To understand details of supersymmetry breaking, we need to know these metrical structures as well, and to see how these geometries are corrected in string theory. These so-called alpha prime corrections require knowledge of the metric. So as I said, we don't have analytic expressions for these things. To date, the best we can do is numerics, and so far the numerics aren't good enough to calculate things like the mass of the electron. They're just sort of good enough to maybe just start exploring. And I'll be more precise about this as the talk continues. So we need a metric to do a lot of interesting phenomenological physics. So we'll discuss how to get a metric now. So this idea of finding numerical metrics has had a fairly long history. People have been working on this problem at some level since the late 80s. But in the early 21st century, there's been quite a bit of progress on this. And in particular, machine learning entered into the story in around 2019, and I've been involved in using machine learning in order to find flat metrics. So I'll talk a little bit about the two references I've given in blue. Okay, so let's just review a little bit of topology. Topology essentially describes structures of geometry, structures of spaces, without knowing metrical details. So an example of a geometry which is flat, but has a non-trivial topology is just a torus. There's an A cycle and a B cycle. The torus has a hole in it. So the A cycle is the cycle which is contractible on a solid torus, and the B cycle describes the hole that we see in the geometry. Now, it turns out that because of, if you think about a fundamental region on the complex plane, and you employ periodic boundary conditions, so that if you hit the top boundary, you return at the bottom, and if you hit the left boundary, you return on the right, the torus has a fundamental domain which can be drawn on the complex plane. And we know that the complex plane admits a flat metric. So the torus admits a flat metric as well. The analytic flat metric was only written down for the torus in 1873. So even though this is an obvious result, it took a little bit of time for people to realize its importance and in mathematics. So the picture of the torus is an example of a Calabi-Yau one-fold. We're talking about Calabi-Yau three-folds. So the Calabi-Yau one-fold is one complex dimensional or two real dimensional. Similarly, the Calabi-Yau three-fold will be three complex dimensional or six real dimensional, so that 10 minus 6 equals 4, the 4 dimensions that we see. So the torus has two different kinds of parameters. One parameter is called the Kähler parameter. The other parameter is called the complex structure parameter. The Kähler parameter describes the area of the torus. So we draw a region of the fundamental domain of the complex plane, and the area of this fundamental domain is the Kähler parameter of the torus. It describes the size of the geometry. The complex structure parameter describes the shape. So the shape here is essentially given by the tilt of the fundamental domain in this the complex plane. So this tau parameter I've drawn is the complex structure parameter of the torus. So the torus has one size parameter and one shape parameter. The geometries we'll study have more such parameters. So we'll look at a particular class of Calabi-Yaus. These are called complete intersection Calabi-Yaus. We think about the zero locus of a set of homogeneous polynomials over coordinates in projective space. And this describes a Calabi-Yau geometry, provided certain mathematical conditions are realized. Well, let's not go into the details here. Let's just say that if you think about polynomial equations and thinking about intersecting solutions to a set of polynomial equations, that intersection can describe a geometry, and that geometry can be Calabi-Yau if certain conditions are satisfied. So the simplest example is the geometry that I showed to you earlier, this quintic hypersurface in four-dimensional complex projective space is an example of a Calabi-Yau. And there's one equation here, u to the fifth plus v to the fifth plus x to the fifth plus y to the fifth plus e to the fifth equals 0. So solutions to that equation are what describe this Calabi-Yau space. So this is going to be an example that we will study, but there are many other geometries that we could study in the story as well. So all of the examples, the torus, the K3, and the various quintics we'll discuss are given by a single equation. So I've written down a number of these equations. The quintic, the Calabi-Yau threefold we'll be looking at, has topological numbers h11 equals 1 and h12 equals 101. So h11 equals 1 means there's one Kähler parameter we associate to the size of the geometry, and h12 equals 101 means there are 101 complex structure parameters. They're the analogs of these taus that we saw for the torus. We can also look at other polynomial equations that are written down, maybe slightly more complicated. Tian-Yau is an example where there is more than one equation, and we have three simultaneous equations we need to solve. And this is actually one of the first Calabi-Yaus that's used for model building, for constructing standard model-like theories that we'll study. Okay, so let's talk a little bit about how to get a metric. So the Calabi-Yau manifold is complex and it's scalar. So its metric is obtained by a function which is called the scalar potential, and derivatives of this function describe the metric on the space. So there is a holomorphic coordinate, which is unbarred, and an anti-holomorphic coordinate, which is barred. So for example, on a torus, we'd have G, Z, Z bar being non-zero, where Z and Z bar are X plus IY and X minus IY on the plane. So if we take derivatives of the scalar potential, or logarithms of the scalar potential, in fact, we get the metric. The metric is then used to construct what's called the scalar form. The scalar form turns out to have a property that it's closed. The exterior derivative acting on this form gives us 0. So that's a condition we need to require in order for the metric, for the geometry to be scalar. And we'll have to ensure that whatever numerical methods we apply respects this property. And then because the metric turns out to be Ricci flat, the Ricci tensor constructed from the metric has to vanish. The Ricci tensor on these spaces has a very nice expression. We take the determinant of the metric we wrote previously from the scalar potential. The logarithm of the determinant is some quantity we can study, and derivatives of this logarithm have to vanish. Okay, so the formal definition of Calabi-Yau is that of these flat metrics is given by Yau's theorem. Yau's theorem says that in every scalar class, there are as many scalar classes as this topological number H11 that we talked about. For every scalar class, there is a flat metric. So R, A, B bar will vanish for some metric in each scalar class. And as we said, Yau's proof of the existence of this thing is not constructive. It's just mathematical proof that such a thing exists. And it's described in terms of solutions to a classical Monge-Ampère equation. So I'm currently in Paris. I was just on Rue Monge and for lunch, and this equation was written not so far from where I'm sitting. The solutions to this equation is what Yau established mathematically. Okay, so how do we obtain these metrics? So until recently, the best way of doing this was using Donaldson's algorithm. So Donaldson's algorithm says, let's start with a metric on the space in which our Calabi-Yau is embedded. So for example, I have this quintic hypersurface in 4-dimensional projective space. Let's start with a metric on the projective space, and let's see what the pullback of the metric is onto the Calabi-Yau that we're studying. It turns out that the pullback is not Ricci flat. You can already see this for the torus, for example. If you think about the torus as a hypersurface given by a similar equation embedded, this time not in 4-dimensional projective space, but in 2-dimensional projective space, and you employ the same sorts of ideas, you'll find that the metric induced by the embedding of the space into the geometry is not going to be a flat metric. So you need to manipulate the metric you obtain in order to get the flat metric that's the metric that's inherited from having this fundamental domain on the complex plane. So the metric we have on the geometry that's induced by the embedding is a starting point for our construction. And what Donaldson's algorithm does is it looks at various scalar potentials that give us these acceptable metrics, and then iteratively it leads us towards the Ricci flat metric that exists in each scalar class. So we construct these scalar potentials, and then this index little k is something which we'll deal with iteratively. And at each iteration, you step k up by 1, and you get a better and better approximation to this Ricci flat metric. So the idea is to proceed iteratively until you obtain some balanced metric, and the limit of infinite k, this balanced metric, gives us the Ricci flat metric. Now, people have developed numerical implementations of this Donaldson's algorithm. However, these numerical implementations are all computationally very expensive. They scale as say the fifth power of k, for example, for the quintic, and as a result, to get these is difficult. There's a question. Please ask. Yes.
I just allowed Hannes, you can unmute yourself and ask your question. Okay. I'm not sure. Maybe it's a hand which was raised by mistake.
Okay, just keep going. And if there's a question, please interrupt me.
Okay.
So there's a numerical implementation of this Donaldson's algorithm. It's just very difficult to enact in order to get results in a reasonable time. But it provides a baseline for comparison for these machine learned metrics that we'll discuss. So there are different kinds of machine learning. One of the easiest kinds of machine learning is supervised machine learning, in which you present a neural network, say, some input, and based on some examples, you teach it what the output should be. Here, we don't know what the flat metric should be for these Calabi-Yau threefolds, for example. So there's no way to do this as a supervised problem. Rather, we can construct a loss function such that the loss function is minimized when we achieve the flat metric. So the way we'll do this is we'll have a bunch of terms that are all positive, and they're actually zero in the case that we're looking at the flat metric. So as we minimize the loss, our metric becomes flatter and flatter, and eventually when the loss is zero, we're at the flat metric numerically. So in order to do this, we'll look at different measures, and we'll have to have our loss function being a sum of all of these measures. One measure we'll use just simply measures the flatness of the metric. And we'll do this in a slightly cleverer way than just looking at the Ricci tensor, because the Ricci tensor involves taking derivatives, and taking derivatives is an expensive operation numerically and also leads to inaccuracies as you proceed. So we'll construct a measure which compares the volume of our Calabi-Yau. Is computed in two different ways. One way is metric independent, and that's just by looking at the top holomorphic and anti-holomorphic forms. We know that because we have Calabi-Yau geometry, there's a holomorphic 3 form. Similarly, there's an anti-holomorphic 3-bar form, and the wedge product of the 3 form with the wedge product of the 3-0 form with the 0-3 form integrated over the manifold gives us an expression for the volume. Similarly, we can write the volume by integrating the Kähler form, which is a 1-1 form, wedged with itself twice. So the expression for the Kähler form invokes the metric. So as a result, we have two different expressions of the volume, should record the same result. One is metric-based, one is metric-independent. If you compare the two and you subtract one from the other effectively, when that subtraction gives you 0, you're at the flat metric, because you need the flat metric in order to write down this Kähler form. So that's one component of our loss function. A second component of our loss function is the requirement that the Kähler form be closed. So we figure out what that means mathematically, and we require this happens. So that's another component of the loss function. We need to ensure that the metric, that the manifold remains a Kähler manifold. And finally, because we're working with manifolds, we need to ensure that whether we're working in one coordinate chart or another coordinate chart, on the overlap, the metrics will agree. So we can go from one coordinate system to another coordinate system by using a Jacobian to enact the change of coordinates. So if we look at two patches on their overlap, we do a change of coordinates, the metric on each patch must agree. So there's a compatibility measure that is minimized when the the numerical metrics are the same on these two different patches. We're working with the Fermat quintic to start. So in the Fermat quintic, there's only one Kähler class, but there's more than one Kähler class. We have to have additional components of the loss function that ensure that we remain in the same Kähler class as we proceed. So we can just construct, some loss function that has all the nice features we want, so that when the loss function goes to 0, we're at the Ricci flat metric on the Flabiat. So that's our strategy. So proceeding, we'll look at a decomposition of the metric. Metric is a Hermitian matrix. These Hermitian matrices can be decomposed in terms of a diagonal matrix and a lower triangular matrix with ones along the diagonal. And we'll give the neural network the metric of points on the manifold. The metric we'll give it is the metric induced from the embedding. And we'll work to ensure that at those points we've considered, the metric is as flat as possible by minimizing the loss function. And then we'll query this trained neural network on new points, and we'll measure flatness at these new points that we query. So this is how we developed a neural network to find this flat metric. This is work that we did in 2020. We've since refined this and gotten better metrics. And in parallel, these other groups have also done similar investigations. So now there are multiple ways of doing this using machine learning with neural networks. So we sort of outlined what a neural network was before. We look at some input vector, and we consider some layers of neurons, and these layers of neurons, in going from one layer to the next, we've got these weight functions, these bias vectors, and we have these nonlinearities we introduce. And this is all input in Mathematica, so you can just use essentially these techniques out of the box these days. Our implementations use TensorFlow and are written in Python, but these days you can do this in Mathematica as well. So we have two neural networks. One neural network will be responsible for the diagonal part. One neural network will be responsible for the off-diagonal part, and combining these will get the metric. And we have some architecture that essentially describes the metric at different points in the manifold, and then we'll try to find the weights and biases such that our loss function, which gives us a flat metric, is minimized. So the only thing now I need to describe is how to choose points on our geometry. So the way we do this is we want to choose points uniformly somehow on these spaces. We can think about the embedding space. We have some hypersurface equation, which is in this projective space. We take points in the projective space using the Fubini-Studi metric, which we know in the projective space, and we draw lines between pairs of points. These lines will intersect our hypersurface. When they intersect our hypersurface, they may intersect our hypersurface many times, not just one time. We just choose one of the points where this line intersects the hypersurface. This is a point selection procedure for selecting points on our manifold. It was developed by Schiffman and Zeldich, basically, and this is also implemented numerically many times. So that's how we choose points. So, for example, if we're looking at torus as one of these complete intersection hypersurfaces, these Calabi-Yau one folds, we have some point selection that gives us points essentially uniformly on the torus. And on our Fermat quintic, we have some other point selection that follows a similar idea, and we see the points are distributed with some density. So the colors are essentially logarithms that describe where the point selection is densest and where the point selection is least dense on this particular slice of coordinates. So here I've plotted the real part and the imaginary part of one of the coordinates describing the manifold. And if I were to look at a different quintic, one which is not the Fermat quintic but has an additional piece, we see the point selection changes. So the point selection is responsive to the embedding equation in the higher dimensional space. So we also notice that if we if we look at the curvatures associated to points on this Fermat quintic, the curvature is certainly not uniform. There are places where the curvature is larger and the curvature is less large. And there are very few points, in fact, the curvature is 0, which is what we want for this Ricci flat metric. So the initial seed metric is very far from being the flat metric. Okay, so if we do this for a torus, we'll find that the true flat metric, the predicted flat metric, look roughly the same. The peaks here in these plots are regions of high curvature, which is associated to a coordinate singularity in our geometry. So it's not a physical singularity; it's just a choice of coordinates that means that there are these 3 singular points. But elsewhere, far from the singularities, things look rather flat. If we consider the K3, which is a Calabi-Yau twofold in the same family as the quintic and the torus, we find that the individual measures, the sigma measure describing how these 2 different computations of the volume agree, and these other measures describing the celerity and the compatibility of different coordinate patches, all of these are firstly decreasing, and secondly, the curves agree. The curves are in 2 different colors, in blue and gold. And they agree on the training set of points and the validation set of points, which are chosen independently of the training. If we train just on one of these, we find that the other ones don't necessarily do so well. So the loss function really requires all of these features to be present in order to achieve a flat metric. So if you just train on flatness, you're not going to be very good with compatibility or with celerity. So you need to have the loss function embody all of these physical constraints on the Ricci flat metric on this complex and scalar geometry. Curiously, training on compatibility and training on celerity seem to mirror each other. You get one when you train on the other, but that's not true with a flatness bin. So if we employ all of these features in our loss function and train on a few tens of thousands of points, we find that our metric is tending towards a function which satisfies all of these conditions on the loss functions. All of the individual losses are decreasing as we proceed with the training. And similarly, for more complicated quintics, we see the same phenomena. And we don't need a huge number of points in order to achieve a reasonably flat metric in the story. So one thing we've recently been looking at is finding other ways to get a flat metric. One way is using Ricci flow. Ricci flow is a way of going from one metric to another, which respects the Kähler class condition essentially automatically. It's been used to prove the Poincare conjecture for the 3-sphere. Perelman famously obtained this result. In fact, a more general result from Poincare, the Thurston geometrization conjecture was obtained using this method. The idea is essentially, if you consider some flow equation, which changes the metric along the flow, if you define things so that the fixed point of the flow is the flat metric, then you can try to use the flow itself as a loss function. So this is an idea that we're studying to find different ways of finding flat metric that may be more efficient than the ways we've looked at already. And the success we have is that if you consider this on a torus, it works really, really well. We already knew the flat metric on a torus analytically, so this isn't anything more than proof of concept. But we're working on adapting this to Calabi-Yau twofolds and threefolds. Okay, so I started talking about the standard model, and I emphasized that to understand aspects of the standard model, we need to know what the flat metric is. We now have a bunch of numerical flat metrics. So the question I want to ask in the remainder of the talk is, can we use these existing numerical metrics for phenomenology, or do we need to work harder in order to eventually do phenomenology using these Calabi-Yau metrics? Okay, so I'll start with K3. K3 is the first sort of non-trivial Calabi-Yau. It's a Calabi-Yau twofold. So it's sort of the higher dimensional analog of the torus. I've looked at a particular form of K3. This K3 is called the Cephalou family. First, there is this quartic piece, which is the analog of the quintic piece for the quintic Calabi-Yau that we looked at a few minutes ago. And it's the analog of the cubic that we saw for the torus earlier in the talk. But we deform that piece by adding an extra term. This extra term we add is also a quartic term. It's essentially given to us by the sum of the coordinates squared. You take that sum and you square it. And there's a coefficient lambda, which is in front of this extra term we've added. Variation of lambda preserves the Kähler class of the metric. And there are particular values of lambda, 3/4, 1, 3/2, and 3, in which it turns out this equation is singular. So there's the special points that we'll look at, but we'll look at all possible points for all possible values of lambda as coefficient in this expression. If you like, this is a complex structure we're looking at. Okay, so these singularities are known. They're sort of they're called A1 type singularities, and depending upon which value of lambda we're looking at, there may be different numbers of singular points: 8, 16, 12, and 4 in this case. So the singularity is associated with the polynomial failing to be transverse at these particular values of lambda. And at particular values, 3/4 and 1, we can think about these as related to orbifolds in some sense of either T4 or the space, which is non-singular. Okay, we'll also consider Dwork type deformations of the quintic of K3. So there's a quartic with this extra term which involves psi, which is rather similar to the Dwork quintic we studied in the plots I showed you a bit earlier. So the two kinds of deformations, these Dwork deformations, these Cephalou deformations, they overlap at particular points. Either lambda equals 0, this coefficient lambda in this equation being 0, or the psi being 0, this other equation. So lambda equals 0 corresponds to psi equals 0, and lambda equals 1 corresponds to psi equals 1. So at least at 2 points, these two families will intersect. Again, we've got these conditions on the metric. The metric is complex in Kähler, and the Kähler form is closed, and so on. So we'll use these features. Now, because geometry is Kähler, it has this Kähler form sitting on it, it turns out that differential geometry is a bit easier than you expect, in that a lot of the components of the Christoffel connection and the Riemann tensor just automatically vanish. And I've shown you the non-vanishing components on this slide here. So we don't need to compute everything, we just compute a few things in order to study aspects of what I'll be looking at. So what I'll be looking at is things which are built on the Riemann tensor. We know the Ricci tensor, which is built on the Riemann tensor, is 0 because the metric is Ricci flat eventually, but there are other quantities you can construct the Riemann tensor that are non-zero, and they'll be useful in what I'll say. So in particular, what I'm interested in is what's called the Euler density. The integral of the Euler density over the manifold recovers the Euler class of the manifold, Euler character of the manifold. The Euler character is a topological invariant, so it's independent of the metric. For K3, it turns out the Euler character is 24. You can construct this 24. You can obtain this 24 using purely topological arguments, as I said, because it's topological. But you can also obtain 24 as an integral of the Euler density. The Euler density is given to you by the Riemann tensor. The Riemann tensor is given to you by the metric. So you can also describe this in a metrical way and see how close you get to 24 by looking at the geometric description of the Euler character. So a number of terms will vanish by virtue of the Riemann tensor, the Ricci scalar vanishing, but we can explicitly compute various things. And what we compute is that we can write down the top Chern form. and the top churn form is integrated to give us the Euler character. It describes the Euler density, in other words. And we know that for K3, the Euler character is 24, and for the quintic and P4, the Euler character is minus 200. Okay, so we'll learn the metric using before I was saying we can get reasonably good metrics with 10,000-ish points. Here we're using 500,000 points, and we'll compute these integrals using Monte Carlo methods. We did these calculations and we wrote this paper at the end of last year, and we notice that as before, if we look at various values of lambda and we look at the loss function is decreasing, and we're getting flatter and flatter metrics as we train the network through several epochs. And we can compute the Euler character in different ways. It's topological invariance. We use any metric to compute this, in fact. If we start off with the induced metric from the embedding, we get an answer of 24.23, close enough to 24, which is what we expect. And if we use the flat metric, we get 24.04. So, roughly speaking, for K3, for the smooth K3, we get the answer on the nose. For the singular versions of K3, the story is a little more complicated, but the integral plus expressions that are sort of corrections because of singularities give us 24. So, for example, if you take the second column, the degree of C2, and you subtract from this the degree of C1 squared, that gives us numbers that are rather close to 24, which indicates that the machine learning is recovering essentially the right answer. These are plots of what happens as you approach these singular points. We see that things are relatively smooth, and it's just the singular points are very singular. So if you're very close to a singularity, you're still getting answers around 24, but the answer jumps at the singularity because of the singular structure. This is true for things which are close to 3/4 and things which are close to, say, 3/2. The results at 3 and at 1 are less good. This is not numerical error. This is something physical that's happening, which you don't fully understand. So I'm not going to say very much about this, but we have some speculations about the structure in our paper, and you can look it up there if you like. And we can establish mathematical results using the Euler character that we machine learn in some sense. Okay, so one thing to examine is to look at where the Euler density is concentrated. If you look at the Fubini-Studi metric, which is the induced metric from the embedding, you find that the Euler character is distributed. The churn distribution corresponding to Euler density is distributed somewhat evenly across the manifold, whereas in the flat metric, it's much more tightly peaked. So there are qualitative differences in how the churn distribution is realized in the flat metric compared to the induced metric. And this applies to the singular versions of these geometries as well. So this is something we've studied, and this is sort of a new window into the geometry of these spaces. And we can see the singular structures quite explicitly by studying the Euler density. So the quintic hypersurface, which is the Calabi-Yau threefold that we looked at in some detail earlier, we find that when you compute the Euler character, the answer, which should be minus 200, varies. It's minus 204 is the answer we get from the machine learned metric. So the Euler character here is off by about 2%. So we noticed in the beginning that in the very, very simplest compactifications of string theory, from 10 down to 4 dimensions, the Euler character told us about how many dimensions there were in the low energy effective theory. So there are 3 generations of particles in the Stern model. In these simplest naive constructions, we get this from looking at a geometry with Euler character +6 or -6. You take the absolute value divided by 2. This tells you the number of generations. This corresponds to the index of the Dirac operator on the space. Dirac operator is like the square root of the Laplacian on the space. So in any case, if you're off by 2%, this is not so good in that you're predicting the wrong number of generations of particles on theory, which is compactified on the quintic. So right now, then, if the Euler character is somewhat on the large side, being off by 2% means that you're making incorrect particle physics predictions. So these metrics are not good enough yet then to do phenomenology. However, if you're compactifying on a manifold with a smaller Euler character, maybe being off by 2% isn't so bad. So for example, for the quartic, for the K3, if you're off by 2% at 24 and you round, you get 24 basically. So as a result, the calculation is good enough for those purposes. So depending upon the geometry you're using, maybe these metrics are good enough already, maybe they're not good enough already. More investigation is necessary to figure this out. So let me briefly summarize what we've done and conclude. So we've constructed numerical metrics on K3 and the Fermat quintic using neural networks. And we've noticed that the Euler density clusters near singular loci. We've noticed that these metrics are interesting in that there are some things to figure out about the singular K3s. And given suitably many points and running the code long enough, we find that we can reproduce the Euler character of K3 by looking at the learned flat metric. This is harder to do for three-folds than it is for two-folds, where we're off by 2% at some level. So things to do in the future is to get more points, to get improved metrics, to see what happens, whether we can learn these things better. We can maybe make the loss function clever in order to get flatter and flatter metrics by imposing more conditions. This may be expensive numerically at some level, but it may be beneficial in other levels. So we just see whether these things trade off appropriately in order to achieve proper flat metrics. We can maybe start using these metrics for phenomenology to see where they lead us. These Yukawa couplings, these parameters that appear in the Lagrangian at low energies that required us to know the metric, we can start computing these now. And we can try to see whether these calculations are good enough, because it turns out that the ratios of some of these couplings are known independent of the metric. So we can see whether we recover the right ratios by computing these different quantities. We can also look at particular limits of Calabi-Yau's, where we expect the geometry to have specified forms. So the SYZ conjecture says that in the large complex structural limit of these geometries, you should see that the mirror geometry, so each Calabi-Yau has a mirror geometry, mirror Calabi-Yau. The mirror Calabi-Yau will factorize in terms of a base and a torus, fibred over the base. So we can see whether this vibration structure on the mirror is evident by looking at limits of these Calabi-Yau's whose metrics we know. And we can try to construct flat metrics using Ricci flow. So these are things that I'm working on these days in trying to understand better flat metrics and use these machine learning methods in order to understand the geometry of the extra dimensions as predicted by string theory and use these extra dimensions to do particle physics. And hopefully, as this methodology improves and these techniques refine, we can try to see whether we can reconstruct aspects of particle physics for a genuine string compactification. So I'll stop there. Thank you very much.
Thank you very much, Vishnu, for the very interesting lecture. And okay, so let's see if there is any questions. Participants, please, you can raise your hand and I will give you the right to ask a question. And while you're thinking, maybe I can ask a question because, like you were using Mathematica to do your neural networks, but Mathematica is much more famous for not the numerical calculations, but analytical calculations. And the question is, and this kind of naturally could probably embed some, I don't know, could you do some using neural network to get some analytical formulas from kind of some families of formulas, which probably will be even more interesting?
Yes, that would be great. It turns out that for a particular K3, the K3 associated to T4 mod Z2, where this lambda parameter is equal to 1, that particular K3, there is a known analytic metric. So one of the things we'd like to do is match our numerical metrics to that analytic metric to see whether we can learn something about the structure of these things for K3. There's no similar matching we can do for Calabi-Yau threefolds. There's no analytic results that exist really. So it would be great to get analytic results, but it's sort of a work in progress because you sort of bootstrap this based on the analytic results we have for lower dimensional Calabi-Yaus, and there are very few of those. Yeah, it'd be great to have analytic metrics. We don't really know how to do this yet, but this is something that we would like to think about. Maybe these limits I talked about, where we have these this SYZ conjecture, where we expect the mirror Calabi-Yau to be some base with a torus fibered on top. We know the metric on the torus, of course, so maybe we can try to understand something analytic based on that. But really going from, so one of the difficulties in matching our numerical metrics to the analytic metric on this T4 mod Z2 example is simply coordinate systems. The coordinate system that we have in numerics is not the same as the coordinate system for the analytics. So you need to find the appropriate rotation to take one coordinate system to the other coordinate system. It's not, it's a complicated function that takes you from one to the other. So until you figure out that relation between coordinates, it's even hard to do a comparison.
Okay. Thank you. Because yes, like when I hear that you do stuff in Mathematica, that was my natural thing, because kind of one could really think how to embed it, because Mathematica will be naturally good at that things, and you don't need to kind of add extra on top if you would do it, I don't know, in the TensorFlow or in the.
Well, we mostly use TensorFlow to do these things. We don't really use Mathematica for the most part. I mean, Mathematica is sort of a front end for some of these things, but it's not really where the guts of the calculation is taking place.
Okay. I don't see any questions. Maybe people are a little bit shy today, or maybe they need a little bit time to digest the material. But I'm sure that if there will be questions, they can contact you. And because the talk will be available. There is a question. Okay, Hector, you can unmute yourself.
Can you hear me?
Yes.
Just out of curiosity, what if you were to study different Taylor manifolds, for instance, like a conformal manifold for these N=4 super Yang-Mills gauge fields, families of those? Would this method be applicable in that case?
Sure. These methods are applicable. You can find metrics on these spaces. We haven't done this, so I can't really speculate as to what we would find, but certainly we can apply these techniques to other geometries as well.
Okay, as long as they're Kähler, right?
Well, I mean, if it's not Kähler, you can find some other condition you want to respect. So people have started looking at G2, for example, finding flat metrics on G2 manifolds. This is sort of early days, so I'm not sure people have done this or have results to report yet. I don't have any results to report for G2, for example, but in principle, you can start doing this kind of thing for lots of geometries.
Okay, thank you.
Okay. I do not see any other questions, so I think my job is to thank you, Vishnu, very much for the very nice talk. And as I mentioned before, the talk will be online fairly soon. And of course, everyone is invited to the next lecture of this mini school, which will be on the machine learning of the many body localization, a practical introduction, which will be given by the Cameron Beetar next week. Okay.
There's one
Thank
more
you very
question,
much.
it looks like. There's one more.
Yes. Yeah. Tato.
Yes, greetings and thank you for the wonderful lecture. I just wanted to understand how can we improve on the phenomenology, and when we postulate a hypothesis based on the phenomenology, what are the innovative way we can be able to take looking at the K3 and looking at the how neural networks use a variety of step functions, and then looking at the type of learning, whether it's supervised or unsupervised or reinforced. So on the phenomenology, how could we look at that approach and then to understand the postulation of the hypothesis so that we have a harmonic equilibrium with regards to the output of the postulation of the phenomenology? Thank you.
Okay, so I want to sort of decompose that question. The first question is, what is phenomenology? Phenomenology is just to find some way of understanding the structures that we see in nature. So nature has 3 generations of particles, and these particles have certain masses that you can look up. So you can look up masses for the up quark, the down quark, etc. All these particles have spectra with masses and so on. So the first thing you want to do is to reproduce the masses of the particles in the context of a theory such that we reproduce the interactions that are seen in the standard model. So what string theory is right now is that there are various constructions, say roughly 10,000 constructions of these type, where we choose some calabi-Yau or some structures on these calabi-Yaus, and these calabi-Yau spaces with these structures on them maybe give us a Lagrangian which has all the terms we expect in the standard model Lagrangian. So it tells us that, for example, there's a mass term for the electron. There's a term which describes how the electron couples to the photon. There are all of these terms that are sort of present in our Lagrangian. We don't know in this Lagrangian are the coefficients. How strongly does an electron interact with a photon? How strongly do these masses, how big are these masses, for example? In our description of nature, there's one light generation, which consists of the up, the down, the electron neutrino. And then there's a heavier generation with the charm and the strange and the muon neutrino, and a very heavy generation with the bottom, the top, and the tau and the tau neutrino. Is it natural, or how often is it the case that when we look at these Yukawa couplings and these different string constructions, how often is it the case that we have these hierarchies between the generations and their masses? We don't know, but this is a question we can in principle start answering now that we have these metrics. Try to compute these couplings and see whether they segregate into a light family, a medium family, and a heavy family. And that's a question that we couldn't answer before. Now we're able to answer that question maybe. As far as making more contact with experiment, that'll take longer and longer effort. And we're still in the baby steps here. We're trying to see whether these models actually match standard model Lagrangian at all. And if none of these models we have one light generation, one medium generation, one heavy generation, then none of these models are correct. And we should find some better model. But that's a question we couldn't even answer before. But we're able to make some progress on this now. And that's the hope in the next few years anyway, that we'll start being able to look at these kinds of questions.
Thank you. That was quite informative. We will also look into it in the future. Thank you.
Okay.
Okay. So, okay. I don't see any more questions, so we need to thank the speaker again. Thank you very much for the very nice talk. And as I mentioned, next week we're going to have a next installment of the mini school. Thank you very much.
All right.
Bye-bye.